Right now, as you're watching this video, you're hurtling through space at over 500,000 miles per hour. You're spinning, tumbling, and racing through the cosmic void on a journey so vast that your mind will struggle to comprehend its true scale. You're traveling aboard a tiny blue marble that orbits an ordinary star nestled within one of the spiral arms of an absolutely colossal structure called the Milky Way galaxy. Here's what should make your brain tingle with wonder. Despite living inside this cosmic behemoth our entire lives, we've only recently begun to grasp just how monumentally massive our galactic neighborhood truly is. Before we dive into this cosmic adventure together, I'd love to know where in the universe you're tuning in from tonight. Drop a comment and let me know what time it is in your corner of our pale blue dot. And if you find yourself drawn to these explorations of cosmic scale and wonder, I'd be incredibly grateful if you subscribe to Stellify Science to join our growing community of cosmic explorers. Get ready, the journey begins now. Tonight, we're embarking on a journey each. Milkometa could extend for 400,000 light-years or more in diameter. The combined dark matter halos of the two galaxies will create an even more extended structure, potentially reaching across more than one to understand the true scale of our cosmic home. We're going to explore a structure so enormous that light itself, racing at 186,000 miles per second, takes over 100,000 years to cross from one side to the other. We'll discover how astronomers solved one of science's most challenging puzzles: measuring something when you're trapped inside it. This is the story of humanity's greatest measurement challenge: million light-years of space. This future transformation provides important context for understanding current measurements of galactic scale. The Milky Way we observe today represents just one phase in a cosmic story that spans billions of years: the galaxy's current size. Imagine trying to determine the size of a vast city while blindfolded and placed somewhere within its boundaries. You can't see the edges. You can't fly above it for perspective, and you're limited to observations from your instructor reflect its particular evolutionary history. But they also foreshadow dramatic changes that lie ahead. Understanding these future changes requires sophisticated computer models that can simulate galactic interactions across cosmic timescales. These simulations reveal that galaxy mergers are fundamental drivers of cosmic evolution, fixed position. That's essentially the challenge astronomers faced for centuries with the Milky Way. By the end of this journey, you'll understand not just its size, but how that measurement revolutionized our understanding of our place in the cosmos. You'll discover that the Milky Way isn't just big. It's so vast that it contains somewhere between 100 and 400 billion stars, each potentially hosting its own family of worlds. The quest responsible for creating the largest and most massive galaxies in the universe. The Milky Way Andromeda collision represents just one example of these cosmic interactions. Throughout the universe, galaxies are constantly merging and evolving, creating an ever-changing tapestry of cosmic. To understand our galactic home began thousands of years ago, long before telescopes, before we even knew what a galaxy was. Ancient civilizations saw a ghostly band of light stretching across the heavens. They had no idea they were looking at the combined glow structure. The techniques developed to study our own galaxy's merger history and future evolution are being applied to understand these processes on much larger scales. But perhaps the most profound implication of measuring the Milky Way's scale is what it reveals about our cosmic context. Every refinement in our understanding of galactic size places humanity in an ever-expanding hierarchy of cosmic structure that challenges our most basic assumptions about our place in the universe. We live on a planet orbiting an ordinary star, located roughly halfway out from the center of a galaxy that spans hundreds of thousands of light years and contains hundreds of billions of stars. This galaxy is itself just one member of a small group of galaxies that occupies a tiny corner of a much larger cosmic of billions of distant suns, all part of the same colossal structure that contained their world. The ancient Greeks called it Galaxias Kyklos, the Milky Circle. Other cultures had their own poetic names, but no one understood what they were truly seeing. For millennia, that faint river of light remained one of the universe's greatest mysteries. The truth would prove far more extraordinary than any myth. The first breakthrough came in 1610, when Galileo Webb extending throughout the observable universe. The numbers involved in these cosmic scales strain human comprehension. If you could somehow travel at the speed of light, the fastest possible speed in the universe, it would take you over 100. Galilei turned his primitive telescope toward the Milky Way. What he discovered changed everything. That ghostly band of light wasn't a cloud or a river. It was composed of countless individual stars, so distant and numerous that they blurred together into a Yunzuan years just to cross from one side of the Milky Way to the other. To reach the Andromeda Galaxy, you would need to maintain that impossible speed for more than 2.5 million years. These vast distances mean that when we observe distant parts of our own galaxy, we're seeing them as they existed in the past. Light from the galactic center shows us conditions that existed 26,000 years ago, when early humans were creating the first continuous glow when viewed with the naked eye. Yet, even Galileo's revolutionary observation only scratched the surface. How many stars were there? How far did it extend? And, most puzzling, what was our sun's relationship to this vast cave paintings? Light from the outer edges of the galactic halo carries information about stellar populations as they existed hundreds of thousands of years ago. In effect, every measurement of galactic scale is also a journey through cosmic time, the Milky Way. We Stellar Collection, answering these questions would consume the next 3 centuries of astronomical research. One of the first serious attempts to map our stellar neighborhood came from William Herschel in 1785. Herschel, who discovered Uranus, embarked observed today is not a single instantaneous snapshot, but rather a composite image built from light that has been traveling toward us for thousands or millions of years from different regions of the galaxy. This temporal aspect adds another layer of complexity to understanding galactic structure on an ambitious project to understand the shape and size of the Milky Way. His method was simple. He counted stars in different directions across the sky. If he saw many stars, the galaxy probably extended farther in that direction. Fewer stars suggested an evolution. The galaxy is not a static object, frozen in time, but rather a dynamic system that changes continuously as stars are born and die, as gas flows through the spiral arms, and as gravitational interactions reshape the overall structure. Modern astronomy, a closer edge. By systematically counting stars, he could map its rough shape and size. What Herschel discovered was revolutionary. The Milky Way wasn't spherical. It was flattened like a disc or wheel, and far larger than anyone had imagined. Is beginning to capture this dynamic nature through time domain surveys that monitor millions of stars simultaneously, tracking changes in brightness, position, and motion over periods of years or decades. These observations reveal a galaxy in constant flux with stellar explosions. Most surprisingly, Herschel's star count suggested our Sun was located near the center of this vast stellar disk. This seemed to place humanity in a cosmically privileged position, fitting the anthropocentric worldview of the time. However, Herschel planetary transits and gravitational interactions creating an ever-changing cosmic landscape. The most ambitious future surveys will extend these time domain studies over much longer periods, potentially tracking galactic evolution over centuries or millennia. These observations will provide unprecedented insights into how galaxies like the Milky Way change over time and how their measured properties reflect ongoing evolutionary processes. But even as our observational capabilities continue to advance, fundamental questions about galactic scale remain unanswered. The exact mass of the Milky Way is still uncertain's measurements, groundbreaking as they were, suffered from a fundamental problem that wouldn't be understood for over a century. His star counts were systematically distorted by something invisible, vast clouds of dust and gas, acting like cosmic fog, dimming light by factors of 2 or more. The total number of stars could be anywhere from 100 billion to 400 billion. The extent of the dark matter halo remains poorly constrained, with estimates ranging from 300 from distant stars and making them harder to detect. This interstellar dust would prove to be one of the greatest obstacles to understanding our galaxy's true size. Just as earthly fog makes a forest seem smaller, cosmic dust made the Milky Ways in light years to nearly 2 million light years. These uncertainties reflect not just the technical challenges of measuring cosmic scales, but also the fundamental complexity of defining what constitutes a galaxy. As our understanding of cosmic structure continues to appear smaller and artificially placed us near its center, the next major advance came from Dutch astronomer Jacobus Kapteyn in the early 1900s. Kapteyn refined Herschel's approach using improved telescopes and photographic techniques. His to evolve, so too does our conception of where the Milky Way ends and the broader universe begins. The boundaries we measure today may seem well-defined, but they represent our current best understanding of a cosmic system that operates according to physical laws. Work produced the Kapteyn universe, a more sophisticated model suggesting our galaxy was a relatively small elliptical collection of stars about 50,000 light-years in diameter. Like Herschel, Kapteyn's analysis placed the and processes that we're still discovering. Each new observation has the potential to revise our understanding of galactic scale. Just as previous generations of astronomers repeatedly redefined the size and nature of our cosmic home, this ongoing process of discovery ensures that the Sun near its center. But even as Kapteyn refined his model, another astronomer was preparing to shatter our understanding of cosmic scale, Harlow Shapley. His approach would prove far more revolutionary than simple star counting. Shapley focused on globular story of measuring the Milky Way's scale will continue for generations to come. Future telescopes will push the boundaries of observation farther than ever before, potentially detecting individual stars throughout the local group and beyond. Advanced computational models will simulate galactic evolution with clusters, dense, spherical collections of ancient stars orbiting the Milky Way like satellites. What made them useful was their visibility at enormous distances, far beyond individual stars. Using the 60-inch telescope at Mount Wilson Observatory, Shapley began a systematic study, unprecedented detail and accuracy. Most importantly, these future discoveries will continue to expand our cosmic perspective, revealing new layers of complexity and beauty in the universe around us. The Milky Way, vast as it appears today, may prove to be just the beginning of a cosmic story, whose true scale we're only beginning to comprehend. As we stand at the threshold of these future discoveries, we carry with us the accumulated wisdom of generations of astronomers who dedicated their lives to understanding our place in. He discovered the clusters weren't evenly distributed, as expected if the sun were at the galactic center. Instead, they were heavily concentrated toward the constellation Sagittarius. Shapley's interpretation was bold and correct. The globular clusters, the cosmos. From ancient stargazers, who first wondered about the nature of the Milky Way, to modern researchers using space-based telescopes to map dark matter halos. Each generation has pushed the boundaries of the known a little farther. The measurements we've achieved formed a roughly spherical halo around the true center of the Milky Way. Their concentration in one direction meant we weren't at the galactic center at all. We were displaced, located in what we now call the galactic suburbs, roughly 30,000 light-years from the true galactic center. This was a profound realization for humanity's cosmic status. We weren't at the center of the universe, or even our galaxy. We occupied and off humanity's greatest triumph in understanding cosmic scale. We've learned to see beyond the limitations of our earthbound perspective, to peer through cosmic dust and across vast distances, to detect the invisible influence of dark matter, and to reconstruct the history of our galaxy's formation and evolution. But perhaps the most remarkable aspect of this achievement is that it was accomplished by creatures who evolved on a small planet, orbiting an ordinary star in an unremarkable region of galactic space. Through ingenuity, center position in what Shapley determined was a much larger stellar system than previously imagined. His measurements suggested the Milky Way was roughly 100,000 light-years in diameter, nearly twice Kapteyn's estimates. More revolutionary persistence and an insatiable curiosity about the cosmos. We've managed to map the structure of our entire galactic home, despite being trapped within its boundaries. This accomplishment stands as testimony to the power of scientific inquiry, and the remarkable capacity of conscious was the implication that our sun was just one ordinary star among hundreds of billions in an unremarkable region of galactic space. Shapley's 1917 results marked a turning point. Humans had a reasonably accurate picture of our galactic beings to understand their cosmic environment. In measuring the Milky Way's scale, we've not only learned about the universe around us, but also demonstrated our species' unique ability to transcend the limitations of our immediate environment through observation, reasoning home's size and our position within it. But his work also raised new questions. What lay beyond its edges? Were there other stellar systems? How could astronomers refine their understanding while trapped inside it? The answers would require new technologies and imagination. The story of cosmic measurement continues, driven by the same curiosity that first led ancient astronomers to wonder about the nature of that ghostly band of light stretching across the night sky. Each new discovery adds another chapter to humanity's growing understanding of our place in a universe far stranger, more beautiful, and more vast than our ancestors could have dreamed. Tonight, as we reach the culmination of our cosmic journey through the Milky Way's immeasurable scale, we must ways of thinking. In the 1930s, a crucial piece of the puzzle fell into place when astronomer Robert Julius Trumpler solved the mystery that had plagued galactic measurements since Herschel's time. Trumpler studied confront a truth that will forever change how you perceive your place in the universe. Every number we've discussed, every measurement we've explored, every boundary we've attempted to define represents humanity's most audacious attempt to comprehend something star clusters, and found that distant ones appeared redder than expected. This reddening was precisely what you'd expect if starlight was filtered through dust. Trumpler had quantified interstellar dust absorption, the invisible factor distorting measurements for centuries. This so vast that it challenges the very nature of what it means to truly understand cosmic scale. But here's what should make your mind reel with wonder, and perhaps a touch of cosmic vertigo. All of these measurements, all of this accumulated knowledge revolutionized galactic astronomy. Once astronomers could account for dust, they could correct distance measurements and get a clearer picture of the galaxy's true structure. The Milky Way emerged from the cosmic fog, revealing its actual scale and organization. With dust effects understood about our galactic home, has been gathered by beings whose entire existence spans less than the time it takes light to travel from one edge of a single spiral arm to another. We are mayflies attempting to map eternity. Yet somehow, the modern picture took shape. Our galaxy was a vast, flattened disk of stars, roughly 100,000 light-years in diameter. It had a central bulge of older stars, spiral arms where new stars were born, and succeeded beyond our wildest dreams. Consider the profound irony of our situation. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in the nuclear furnaces of stars, scattered throughout this vast galactic structure over billions of years. You are not separate from the Milky Way. You are the Milky Way, temporarily organized into a form capable of contemplating its own cosmic origins. This realization transforms our entire understanding of what it means to an extended halo of globular clusters and dark matter, reaching far beyond the visible stellar disk. However, measuring the Milky Way's size from our embedded position remains an enormous challenge. Imagine mapping a vast forest from within, where nearby trees are clear measure galactic scale. We're not external observers studying a distant object. We are the galaxy studying itself. Matter organized into consciousness through billions of years of stellar alchemy and planetary evolution. Every telescope we build, every calculation we make, every moment of but distant ones blur. Astronomers face this problem. They use parallax for nearby stars, measuring apparent shifts as Earth orbits the Sun. But parallax only works for a few thousand light years. For more distant objects, astronomers rely on wonder we experience. While contemplating cosmic distances represents the universe's attempt to understand its own structure through the temporary arrangements of matter we call human beings. The measurements we've achieved place us within a cosmic hierarchy so vast that it defies human standard candles, objects with known intrinsic brightness. By comparing an object's apparent brightness with its known true brightness, they determine distance. The dimmer it appears, the more distant it is. But finding reliable standard candles is challenging as intuition. Our solar system, which seemed enormous when we first began exploring it with spacecraft, occupies a region of space so tiny compared to the galactic disk that it would be invisible even in the most detailed maps of galactic structure. The distance from the Sun to Pluto, once considered the edge of our cosmic neighborhood, spans roughly 12 light hours. The Milky Way spans 100,000 light years. To put this in perspective, if you could, star brightnesses vary with type and age. Dust absorption further complicates calculations by affecting different wavelengths of light differently. Despite these challenges, astronomers have gradually built a detailed map, identifying spiral arms, gas and dust distribution, and star-forming regions. They shrink the entire solar system down to the size of a single cell in your body. The Milky Way would still be larger than North America. That's the scale we're dealing with when we attempt to comprehend our galactic home. Yet painstaking methods would reshape our understanding of cosmic scale forever. As instruments and techniques improved, a more complex and vast galaxy emerged. A major breakthrough came with radio astronomy in the mid-20th century. Unlike visible light, radio waves somehow, through centuries of patient observation and brilliant theoretical insights, we've managed to map this colossal structure with remarkable precision. The techniques that made these measurements possible represent some of humanity's greatest intellectual achievements. We've learned to penetrate dust clouds, allowing scientists to peer through cosmic fog and map our stellar home's true extent. Radio telescopes revealed something extraordinary. The Milky Way had elegant, sweeping spiral arms, graceful curves of stars, gas, and dust winding outward from the use of the parallax effect, measuring the tiny shifts in stellar positions as Earth orbits the Sun to determine distances to nearby stars. We've discovered standard candles, objects whose intrinsic brightness we can calculate, allowing us to gauge distances throughout the galaxy center. These weren't static features, but dynamic regions where interstellar gas was compressed, triggering new star births. Radio observations showed continuous star formation, with each spiral arm a stellar nursery. But the most startling discovery was how much of the galaxy had been. We've developed radio astronomy to peer through cosmic dust, revealing the elegant spiral structure hidden from optical telescopes. Perhaps most remarkably, we've learned to use the galaxy's own gravitational field as a cosmic laboratory. By studying the hidden, radio maps revealed the Milky Way extended much farther than visible light surveys suggested. What seemed to be the galaxy's edges were just the limits of what could be seen through the dust. As radio astronomy matured, it became clear our motions of stars, gas clouds, and satellite galaxies. We can map the distribution of matter throughout the Milky Way, including the invisible dark matter that comprises most of its mass. We've turned our galaxy into a vast experiment in gravitational physics, using stellar orbits to probe the fundamental structure of space and time. These achievements become even more extraordinary when you consider the observational challenges we've had to overcome. Imagine trying to map the layout of a vast city while blindfolded. Galaxy was truly enormous. The visible disk was merely the bright center of a much larger structure. Radio observations pushed the known boundaries outward, indicating a significantly more massive and extensive galaxy. By the 1970s and 1980, located somewhere within its boundaries, with dust and fog obscuring your view in every direction. That's essentially what astronomers have been doing for centuries in their quest to understand galactic structure. The interstellar dust that fills the galactic disk absorbs and scats. Astronomers had a reasonably complete picture: a barred spiral galaxy, roughly 100,000 light years in diameter, containing 100 to 400 billion stars, and embedded in a much larger darkness light from distant stars, making them appear dimmer and redder than they actually are. This cosmic fog had been systematically distorting distance measurements for decades before astronomers learned to account for its effects. Even today, dust absorption remains one of the matter halo, extending perhaps 10 times farther than the visible stars. But even these impressive numbers were about to be dwarfed by discoveries that would push galactic scale far beyond anything previously imagined. The key insight came from studying something invisible, primary obstacles to observing the galaxy's most distant regions. But we've developed ingenious methods to overcome these limitations. Radio waves can penetrate dust clouds that completely block visible light, allowing us to map the distribution of hydrogen gas throughout the galaxy. Infrared telescopes can detect the heat radiation from dust grains themselves, revealing the structure of star-forming regions hidden from optical view. Space-based observatories eliminate the blurring effects of Earth's atmosphere, providing the precise measurements needed to detect dark matter. It revealed itself through gravitational effects on visible stars and gas. Mapping stellar motions. Astronomers found stars in the outer galactic disk moved much faster than expected from visible matter alone. According to physics, outer stars should orbit slower, like stellar motions, across vast galactic distances. Each technological breakthrough has pushed our understanding of galactic scale to new frontiers. The Hubble Space Telescope revolutionized our ability to measure distances to nearby galaxies, providing crucial context for understanding the Milky Way's place in distant planets around the Sun. But observations showed stars across the disk moved at roughly the same speed. This could only be explained by much more unseen mass, invisible dark matter providing the additional gravitational pull. Its discovery revealed the Milky Way was far the cosmic hierarchy. The Spitzer Space Telescope mapped the galaxy's infrared emission, revealing its true spiral structure for the first time. The Kepler mission, while searching for exoplanets, provided unprecedented data on stellar populations throughout our galactic neighborhood, more massive than realized. Dark matter observations suggested visible stars and gas were only a small fraction of the galaxy's total mass. The rest was dark matter, undetectable by electromagnetic radiation but revealed by its gravitational influence. This fundamentally changed how astronomers viewed. But perhaps no single mission has transformed our understanding of galactic scale more dramatically than the European Space Agency's Gaia spacecraft. This remarkable observatory has measured the positions and motions of over 1 billion stars with accuracy so extraordinary that it represents a quantum galactic scale. The visible Milky Way was just the bright center of an enormous dark matter structure, extending far beyond the stellar disk. Recent estimates suggest this dark matter halo might extend up to nearly 1 million light-years in radius, making the leap in our ability to map galactic structure. Gaia's precision is equivalent to measuring the width of a human hair from a distance of 1,000 kilometers. The data from Gaia has revealed that our galaxy is far more true. Milky Way, roughly 2 million light-years in diameter. Consider what this means. When you see the Milky Way's ghostly band, you're seeing only the innermost, brightest region of a structure so vast that its true boundaries lie dynamic and complex than anyone imagined. Stars don't simply follow circular orbits around the galactic center, but instead trace complex three-dimensional paths that carry them through different regions of the galaxy over millions of years. Stellar streams wrap around the Milky Way like cosmic ribbons, preserving the archaeological record of ancient galactic mergers that occurred billions of years ago. These discoveries have forced astronomers to completely revise their understanding of how galaxies form and evolve. The Milky Way we observe today is not a primordial structure that far beyond anything visible. We're not just inside a galaxy. We're embedded deep within a cosmic behemoth whose true scale dwarfs our wildest imaginations. Measuring this extended, invisible structure presents immense challenges. How do you map something formed fully assembled in the early universe? Instead, it represents the accumulated result of countless mergers and interactions with smaller galaxies over cosmic time. We live inside a cosmic recycling center, where matter is constantly being reorganized and redistributed through gravitational processes operating over billions you can't see or define the boundaries of a dark matter halo revealed only by subtle gravitational effects. Modern astronomers have developed ingenious techniques. They study the motions of satellite galaxies orbiting the Milky Way, mapping the dark matter halos of years. This hierarchical assembly process explains many of the structural features we observe throughout the galaxy. The central bulge, packed with ancient red stars, formed during violent mergers in the galaxy's youth, when smaller systems crashed together and stirred their gravitational field through their trajectories. They analyze globular cluster orbits, ancient stellar systems tracing paths through galactic space's outer reaches. They even study stellar streams, debris from disrupted satellite galaxies, using these trails as probes of dark matter distribution, stellar populations into a roughly spherical distribution. The thin disk, where most current star formation occurs, developed later as gas settled into a rotating configuration and began forming new generations of stars, enriched with heavy elements from previous stellar generations. The thick disk, containing intermediate-age stellar populations, likely formed during a major merger event roughly 10 billion years ago, when a substantial satellite galaxy was disrupted and its stars scattered throughout the Milky Way's inner regions. The extended stellar halo preserves the debris from countless. Each technique provides a puzzle piece, and combining them reveals a galaxy of staggering complexity and scale. The Milky Way is a multi-layered cosmic ecosystem with distinct regions. At its very center lies Sagittarius AI, a supermassive black hole more than 4 million smaller merger events, creating a complex three-dimensional structure that extends far beyond the visible galactic disk. Understanding this assembly history is crucial for interpreting current measurements of galactic scale, because it reveals that the boundaries we observe today reflect the entire evolutionary history of our cosmic environment. The galaxy's current size depends not just on its initial formation conditions, but on the availability of smaller systems for accretion throughout cosmic time. This evolutionary perspective also provides important context for understanding our galaxy's future. Times the sun's mass at the heart of a central bulge packed with old red stars. Surrounding the central bulge is the galactic disk, where most star formation occurs. This is our location, nestled within a spiral arm about. The Milky Way continues to grow through ongoing interactions with satellite galaxies, and this growth will accelerate dramatically during the eventual collision with Andromeda. The merger will create a galaxy significantly larger than either current system, potentially spanning 400,000 light-years or more in diameter. But even more profound changes may lie further in the future. As the universe continues to expand and galaxy groups become increasingly isolated from each other, the local group will eventually become a closed system 26,000 light-years from the center. The disk has distinct spiral arms winding outward from a central bar. But the disk is also a dynamic system with gas flows, spiral density waves triggering star formation, and stellar associations forming with no external sources of new material. At that point, galactic evolution will be driven primarily by internal processes. The gradual consumption of gas reserves through star formation, the evolution and death of stellar populations, and the slow redistribution of matter through gravitational interactions over truly cosmic timescales measured in trillions of years. Even these internal processes will run their course. Star formation will eventually cease as gas reserves are exhausted, and the galaxy will slowly fade as its stellar populations age and die. The final and dispersing. It's warped, twisted out of a perfect plane by gravitational interactions with satellite galaxies and the dark matter halo. Beyond the stellar disk lies the galactic halo, a spherical region containing globular clusters, ancient stellar streams, and most result will be a collection of stellar remnants, white dwarfs, neutron stars, and black holes, orbiting in the darkness of a universe that has expanded far beyond its current scale. These distant futures provide ultimate context for understanding the significance of our current measurements. We live during a brief golden age of galactic evolution, when star formation continues actively, when spiral structure remains clearly defined, and when the galaxy maintains the elegant architecture that makes detailed observations possible. The measurements we achieve today document of the galaxy's dark matter. This halo extends far beyond visible stars, potentially reaching distances where the Milky Way's gravitational influence overlaps with the Andromeda galaxies. Recent observations, notably from the Gaia spacecraft, have revealed stars and stellar streams exceeding a cosmic structure at its peak of beauty and complexity. As we reach the end of our cosmic journey tonight, remember that every breath you take connects you to stellar nurseries billions of years old. The Milky Way isn't just our address, 300,000 light-years from the galactic center, suggesting the Milky Way's stellar content extends much farther than previously believed. But perhaps the most mind-bending aspect is defining where the galaxy actually ends. Galaxies done in the universe. It's the cosmic story written in starlight and dark matter, spanning up to 2 million light-years of space and time. We've measured the unmeasurable from within, proving that curiosity and ingenuity can't have sharp boundaries. They fade gradually into space, their density dropping until indistinguishable from the cosmic background. Different measurement methods yield different answers. Are we measuring the stellar disk, the dark matter halo, or the last detectable star? Each provides illuminate even the vastest cosmic mysteries. Keep looking up. Don't forget to like this video, share it with fellow cosmic explorers, and subscribe to Stellify Science for more astonishing insights into the universe. Let's a different number, revealing different aspects of our galactic home. The stellar disk, where most visible stars reside, extends roughly 50,000 to 60,000 light-years from the center, giving it a diameter continue to unravel the cosmos together.